The legend lives on from the Chippewa on down of the big lake they call Gitchagumi. The lake, it is said, never gives up her dead when the skies of November turn gloomy. With a load of iron ore, 26,000 tons more than the Edmund Fitzgerald weighed empty. That good ship and true was a bone to be chewed when the gales of November came early. The ship was the pride.
Okay, good morning all. Let me get this turned off so we can get started here. Alright, there we go. Now, of course, we started this off with a little bit of music by Gordon Lightfoot, of course, from his famous song about the sinking of the Edmund Fitzgerald, which occurred in 1975. And we'll get a little more detail of that, student of history here, so we need to learn a little bit about history when it involves materials, especially steels. So we'll get into that maybe a little bit later. But for now, we're going to start with the board I've got drawn up for you this morning. And today we're going to start talking about, we've talked about the properties of steels and the compositions with carbon, et cetera, and looked at, some of the possibilities of being able to heat treat or show what the possibilities of heat treating the three products we could have achieved from heat treating processes. But we're going to talk about specifically about metal alloys and those heat treating processes specifically. And I drew kind of an outline here what we're going to be covering, essentially showing you basically ferrous and non-ferrous metals, and then steel alloys specifically, breaking those down, and then the major alloying elements that are usually added to steels for enhancement purposes, and then we'll talk a little bit about stainless steel specifically. You need to know essentially what its properties are and the types of stainless steels that are out there. And then we'll get into the heat treating methods, both the hardening processes and the softening processes. And then we'll talk specifically about hardenability, what that is, and how we test for hardenability on steels. Okay, so we kind of got a tree going, a family tree here of these alloys. And so metal alloys obviously at the top, and they bifurcated down into either a ferrous, which means obviously the alloy contains iron, or non-ferrous where it doesn't contain iron. And I just listed some of these non-ferrous alloys I'm sure you're familiar with: aluminum, titanium, brass, bronze. Those are all obviously non-ferrous alloys, and we're really not going to get into a lot of detail about those other than that they exist and there are specific applications for those, and a lot of advantages and sometimes not so good advantages, but at any rate we're going to concentrate on the ferrous metals and primarily on steels. We know that from our phase diagram, of course, anything beyond 2% carbon is going to turn into this other product called cast irons. And there's a lot of different types of cast irons. I didn't want to list all of them, but they all have very similar type properties. But we're going to not talk about those as much as we're really going to talk about steels, okay, and how they're broken down. And essentially, they're broken down based on their carbon content into the general category what we're calling plain carbon steels, and they can be broken down into low, medium, and high carbon. And down here I've given you the actual percentages. Generally speaking, most people agree to these percentages, but low carbon steels usually have less than 0.25% carbon. Medium carbon steels are anywhere between 0.25 and 0.6. Now you remember, this is remember how these correlate to the phase diagram and the composition amounts. 0.6 is still not all the way to the eutectoid composition at 0.8. And then we have high carbon steels that are going to be anywhere between zero point 0.6 and 1.5. Now, this is something you need to understand. Most commercially available steels really only go to about 1.5% carbon, even though on the phase diagram it technically says 2%, but really that's usually not the case. Most commercially available steels just go to 1.5% carbon in them for high carbon steels. Okay, so now what I wanted to talk to you a little bit about, then after we get these plain carbon steels, we have another classification called high alloy steels, and inside here you see the carbon then becomes not the main alloying element like it is in these plain carbon steels. There are other alloying elements that we're going to talk about here: chromium, magnesium, molybdenum, nickel. Those are the four that are really added to various steels in high concentrations and high compositions to change a lot of properties. But the two really that they generally lump into stainless steels and tool steels. And of course, tool steels are just the steels that we use for cutting inserts, for cutting tools when we're cutting other particular metals. So they have to be much harder so they can cut a softer type of a steel. So those are very specific. But the one I want to talk to you about in detail a little bit more later on are the stainless steel groups of steels. Okay, so before we get started, we have referenced a lot of times, I think, in the past, the AISI, the American Iron and Steel Institute designation schemes for steels, and essentially consists of 4 digits, 4 numbers, and the first 2 numbers really indicate it's the major alloying elements that are in this particular alloy, steel alloy. And I'll break down those numbers for you here in a minute. I ran out of board here. I have to erase all this. And the second 2 numbers indicate its carbon content in hundredths. Okay, indicate its carbon content in hundredths. So, for instance, if you had something like a 1045 steel, we'll talk about these first 2 numbers. We'll talk about that in a minute and give you specific. But basically, carbon is the major alloying group in this series, the 10 series. But the 45, you would break that down to say that it had 0.45% carbon in it when you see a number like 45. Or a 1018 would have 0.18% carbon in it. Or a 1080 would have obviously 0.8%, which is our eutectoid. So that's what this relates to as far as the second 2 numbers. Anytime you see an AISI steel designation. All right. So let me erase this and tell you a little bit more about some of these alloying groups that exist. All right. So let's look at the major alloying groups here that are available. And okay, these are going to be major alloying groups referencing the AISI designations. Okay, and again, this is the first 2 numbers. Okay. All right, so we're going to have a 10 sometimes, we'll have 11 sometimes, we'll have a 12 sometimes. Basically, all these mean that these are basically plain carbon steels. Plain carbon, which is the majority of steels that you're going to be working with for the most part. And again, these usually have carbon contents, or usually they run from 10, like a 1006, a 1006, or a 1095, something like that. And but these are the and some of these, the reason there's three groupings of these is some of the minor alloying elements change a little bit more than some of these others. So at any rate, that's the if you see a steel and the first two numbers are 10, 11, or 12, you know that the carbon is the major alloying element. Element is carbon. Okay. All right. Now, let's see. There's another series, and if you have a steel that has a 13 or a 15 in them, the major alloying group here will be manganese. Manganese is the major alloying group when you see a 13 or a 15. In the 20s, usually the 23 or 25 grouping, nickel will be the major alloying group here. Then the other ones are, I'm kind of talking about the major alloying elements that I just mentioned: manganese, nickel, chromium, molybdenum. But at any rate, anytime you see a 40s, anywhere in the 40s, all right, I'm just going to put 40s. They're going to be the major alloying group. There will be molybdenum. All right, and we'll talk about these here in a little bit specifically. And then finally, usually in the 50s, the major alloying element will be chromium. Okay, and we're talking a lot about chromium a little bit later on when we get into stainless steels specifically. Okay, so these are the major alloying groups when you see, a steel. So, and for instance, a lot of times you'll see this frequently, a 4140 steel obviously means that molybdenum is a major alloying element, and it has 0.4% carbon in it. Okay, so that's what that means. All right. Now, what I want to do is look at. I want to show you. Let's look at a 1045 steel. I want to show you what they have as far as what's available. When you go and look these things up, this is what you will find, the information specifically on these. And I'm gonna blow this up for you so you can see it a little bit better. But if you look, in fact, I'll make this a little bit larger so we can see it better. I'll just bring it down. But this is a 1045, obviously a plain carbon steel, and it talks about what it's suitable for, and then it starts talking about some of its strength, toughness characteristics. But if you look here now, starts giving these different categories of information. Here's the chemical composition. This is a specific chemical composition of a standard AISI 1045 steel. See, it tells exactly what it is. Even though it says 0.43, this is a rounded number. But here's the other elements in there. And then it starts talking specifically, we'll mention this later when we get into heat treatment, it starts talking about what can be done or how it can be done as far as heat treating processes go. What you have to do to normalize it, what do you have to do to anneal it, okay, and what do you have to do to harden it. And this shows you to heat to 1500, 1600 degrees, water or oil quench, and then temper to appropriate hardness. So those are sort of the main steps. And then it goes so far as talking about applications. This is a really good body of knowledge here. What it's used for: shafts, axles, rods, pinions, gears. Look at this, bulldozer edges. Okay, something very, very hard. So it obviously has a good hardenability rating. but here it talks about machinability. Very important. Whether or not you're trying to machine something like this, you're going to have a little bit of an issue in here. Okay, and there goes the timer. But at any rate, and then about workability. All right, what it can possibly do. As far as hot working, cold working, that kind of thing. So it's a really lot of good body of knowledge of information anytime you pick and choose one of these alloys. And again, as I said before, you know, with respect to the IT diagrams, you know, every one of these alloys will have its own IT diagram. Now, let me show you some effects before I get into the actual talking about the other elements. Let me just show you kind of essentially what's taking place, the net effect of carbon, okay, as it changes, okay. So if you look at the effects of carbon, effects of carbon content, okay, from a diagram standpoint, if we were to put over here, let's see, let's do it this way. Here's one, and we're going to put yield, this sigma yield, and just sigma max over here. And then over on this side, we might put Rockwell hardness scales, okay? All right, so, and then down here will be percent carbon. All right, percent carbon. Okay, and since this is steels, we're really going to go up to about 1.0, okay? And this might be 0.8, somewhere around here. Okay, so if we look at yield strength, you know, down here, and here's the yield strength right here, down here is going to be very low, and as that carbon content increases, so goes the yield strength, all right? And same way with the hardness. Down here, with the low carbon content, does not have good possibilities for having a good hardenability, okay? So as it increases, it gets way up there. And then last but not least, as far as the tensile strength at sigma max, same thing, but it's an even steeper curve as it goes way up here. Okay, so you can see what's taking place here as the carbon content increases. Now let's look on the other side of the coin. The other side of that coin, if we put ductility over here, ductility, all right, ductility over here, and then let's put the IZOD impact strength over here, and again, same thing as far as the carbon content goes, and we're only going to go up to about 1. You can see things start to go the other direction. So up here, with not very much carbon, if we look at the elongation, you know, that percent elongation, ductility, this would be elongation. All right, and then this would be the actual, like, we know that as it elongates, it's going to start to lose its reduction in area, and so the same thing is going to take place. It's going to be a curve that has a really significant amount of reduction, but then it gets smaller and smaller. And then finally, on the IZOD impact strength, same thing, except it's going to be even a lot more steep, the IZOD impact strength. So you can see does not have very much impact strength as the carbon content increases. Okay, so we'll start off the next slide videos on discussing some of these 4 major metallurgical alloying elements, and then we'll get into stainless steels.